So let me introduce the next speaker. The next speaker is Geoff Merrett from the Department of Computer Science and Electronics at the University of Southampton. Geoff is an associate professor there.
Thank you very much, Andreas. I'll just be 1 second. Okay, thank you very much, and thank you for the invitation to speak today. So I'm from the University of Southampton, and my research there really encompasses energy-efficient computing, from Internet of Things like to applications and mobile-like devices, primarily from the perspective of how we manage energy on the systems to make them more energy efficient. And one of the things that we've been looking at for a number of years now is how we can estimate the power consumption or model the power consumption of a CPU at runtime. And it's actually quite interesting looking back when I was putting these slides together. We started probably 3 or 4 years ago looking at this now. And when we first did it, it was from the perspective of Gen 5 that we could get a good model, a good accurate power model into a simulator such as Gen 5. And the progress that we've made over the last few years, we've now got to the point where we've got a good model of power consumption, and we're now getting to that point where it really gets integrated into the simulator and into simulation tools. So it's quite interesting how that process has taken time. But I'm going to talk today really about 2 things. I'll focus to start with on the model itself. I don't think that's at all visible, is it? Nope. I'll focus to start with on how the model itself is built and what our approach is and why it is better than some of the existing approaches that are out there. These tools are open source, and I'll direct you to places where you can find out more about them. And then in the latter part of the talk, I'll talk about how we started to integrate these into Gen 5 and some of the issues that we've come up against and kind of where we've gotten to with the work. So first of all, why do we want to be able to do power estimation, and why do we want to be able to model power? Well, we've been focusing quite a lot through this project, the logo's on the right-hand side of the Prime project, of doing runtime adaptation of systems where we can adapt the operation of the device in order to try and manage energy consumption and quality of service and quality of experience and so on. And there are some systems where your power consumption is known at design time, but where you have event-driven workloads or where you have multiple workloads executed concurrently, you can't make any decisions about this until it's running. And so having a measure of power, whether that is through actual hardware power measurements, or if they're not available, through some kind of software-based power model. Alternatively, power models or knowledge of power consumption is useful in exploring the different designs, whether that is hardware designs and architectures through to software and changes that you make in power management strategies. And predominantly, there's 2 different approaches to power modeling. There's the bottom-up approaches, where you start with the architecture, you start with the specification, you do a simulation of that, and from that, you draw out your model. And these have the advantages that because they're grounded in the specification of the architecture, you can then tweak that architecture and see what effect it has on the power consumption. So very good for the kind of design space exploration process. The disadvantage is typically there are pretty reasonable errors that are associated between the model and what would be likely to be realized in practice. And they're also very slow, so that they can be suitable for the design time approaches, but trying to apply these to runtime management of systems is pretty impossible. The other approach is to come at it from completely the other perspective and take a top-down approach where we start with a particular device, we characterize that device, and we try and form a model or form the relationship between some statistics on the device and the power consumption at that time. The benefit is they tend to be a lot more accurate and lightweight, so you can run them very easily at runtime with little overhead. The disadvantage is it is then customized to that particular device that you've characterized. And it's the second approach here that we use and that we've been looking at through the research so far. So the power modeling methodology that we came up with, which is titled PowerMon. So you start by running a set of workloads on your system. You run them on a practical embedded device. Lots of the work that we've done so far has been on one of the Odroid boards, which contains the quad-core, the octa-core big little device. From that, we record a range of statistics, so performance counters, and then also things like power sensors, voltage sensors, temperature sensors, and so on. We take all of that data, and from it we choose which statistics we want to build our model out of. We build a model, validate that model, and then you have a runtime model that you can use to, first of all, at runtime to estimate your power consumption, but it also tells you various things about your system as well. And I'll talk through. Most of the novelty in the approach is kind of around steps 3 and 4 with a bit of overlap in number 1 as well. And I'll focus in on some of those as we go through. So one of the kind of fundamental viewpoints, if you like, that we come at this work is that lots of the existing literature, and there's quite a lot of work that's published power models based on performance counters. And they all publish their average error, and they all say that they've got a very good average error, and it's a few percent, and therefore this model is the best model ever. And we kind of argue that it's not that is an important statistic, but it's not the only important statistic. And actually the stability of that model, or the ability of the model to work with workloads that it hasn't seen before, and a diverse set of workloads, is actually more important than how well it performs. Because there's no point having one that works very well with one application if that's the only application it works well with. So we would define an unstable model as one that might appear accurate through the testing that they've performed, but if you start to throw other applications at it, it will start to have massive errors and not be at all, not provide a good prediction of the power consumption, whereas a stable model remains accurate across a variety of workloads. Now, to do this, it requires both a careful choice of inputs, so the performance counters, the statistics that we're using, and then also the observations and the training workloads that we use on it. And a nice example of this is if you were trying to build an image sensor and you had to pick 3 inputs that you could use. And then from that, you needed to pick a data set to train and test your image sensor with. You could choose these 3 colors on the left-hand side, aren't particularly representative of the data set that you're going to be trying to capture. More stable model, RGB sensors would be more appropriate in this case. And then the training data set that you pick, if you picked ones that match very well with the inputs you were sensing, you'd get very biased results. Whereas you want to make sure, I'm not necessarily saying these are the right choices, but you want to make sure that your training data set fully tests a diverse set of options that the system is likely to see in the real world. Okay, so for those of you that aren't aware, so PMCs or performance counters are registers in the CPU that count various architecture and microarchitecture events. They are widely available across lots of different platforms and lots of different manufacturers. Not always easy to actually obtain, but they're reasonably low overhead when you do obtain them. And there's lots of different events that are available. So typically, for example, over 70 different events that describe different things going on inside the processor. One of the negatives, however, is that you can't look at all 70 of those at runtime, and you have to pick a smaller number that you can monitor at the same time. And obviously, this is important in the creation of our power model. We've got to pick a small number of monitors that we're going to say represent the diverse operation of our system. So again, in the literature, these are often selected either through intuition, so by thinking about what might contribute to power and so picking them and combining them together. Or it may just be by throwing lots of data at a regression model and seeing which ones seem to provide a good fit. And the problems with these approaches is that you either may not gather a full set of information, you may have a very narrow, you may be gathering a narrow set of information for the workloads that you're training your model with. And also, you might end up picking performance counters that are actually very correlated in what they're measuring. And that isn't necessarily a bad thing in terms of the error, but if you think about 2 performance counters that were very similar and you use them both in your model, and for a particular workload, one could be higher than the other or the other could be higher, and either way you get the same error because they'd be contributing the same thing. If you were to throw a completely different workload at it that would exercise these in a different way, you actually had to get that proportion right in the first place. And so if you just pick lots that are correlated, unless you've tested it with absolutely every workload, you're unlikely to get a model that is stable. So the first part of this approach is then to throw all of the data from those performance counters that have been obtained experimentally across a range of different workloads. And we do hierarchical cluster analysis on it to work out how correlated the different performance counters are. And so this effectively clusters the different performance counters to say these ones are similar or these are correlated. and ones from different clusters are not. And so we can pull them together, and we end up with a set of different clusters indicated by the different colors on here, depending on where you draw the threshold on that previous plot. And then what we aim to do is pick individual performance counters that have a good correlation with power, but from different clusters, and try and avoid picking lots of them from the same cluster. Now, some of you might be skeptical of what I'm saying here about the relevance of a stable model and if it's really required. So I've got a couple of examples here that will hopefully show why it is important to have a stable model. On the left-hand side here, the red bars are from kind of the state-of-the-art approach, building a model based on the kind of principles I said earlier on. And so this is what we're calling an unstable approach, and hopefully you'll see why soon. On the right-hand side, in the blue bars, are the approach that we're taking. And the bars that are shown there at the moment, they've been, the models have been trained using a set of 20 typical workloads that you think that system is going to encounter, and then testing it on the same kind of size of typical workloads. And you see, okay, ours is performing very slightly better, but they're both giving you pretty good accuracy results of under 2.5%. And so in the literature, this is where they say this is a great model, very accurate, a few percent error. If we were then to try that same model, so training it on those same 20 workloads, but now throwing a much wider, diverse set of workloads at it to see how well it actually performs, you'll see that the error gets very considerable. So this model here that looked very good, when running it on unseen workloads, suddenly starts to fall over, and you get 10%-ish error. And in fairness, ours doesn't do much better there. And basically, the small set of non-diverse workloads that it's been trained on mean that it doesn't have enough information to try and accurately predict unseen workloads in a more diverse set. Okay, so instead of just training it on a typical set of workloads, if we were to instead pick a random set from that full 60 and train it on that, so these are the bars marked in blue. If we train it on a small random set and then test it on a random set, the stable model starts to cope a lot better. It's got much more knowledge, and it can pull out much more information about how the power consumption is affected. Interestingly then, if we were to continue to training it just on that random selection, but then test it across our full diverse set of workloads, with the unstable model, it hasn't picked up enough information. The performance counters it's using don't allow it to pull out the information that can actually predict across that variety of workloads, whereas our stable approach means that we get a pretty reasonable model still down at a couple of percent. And actually, if you compare bars D and E, so E is where it was trained on that full set of 60 in the first place versus only being trained on a subset, the error is reasonably the same. So our model is actually able to pick out all of that information and get a good understanding of a much broader set of workloads. Also, if I just compare against some of these state-of-the-art approaches where we've trained it on a set of 20 workloads and then tested it on a broader set, they all have approximately 10% error compared to the real results, whereas our stable model achieves something that's down in these few percent that we're looking for. Once we've selected these performance counters and we've got our stable set, we then have to build our power model, and typically these are done through a regression approach. And the problems with this kind of approach is it's kind of throwing numbers at a curve-fitting model and hoping that it will pull out the correct model. And the way that we propose doing this instead is kind of a halfway between these bottom-up approaches and the top-down. We think about actually where the power is being consumed and provide the appropriate coefficients and splitting it into the dynamic and the static parts to represent those parts of the power consumption in the model. One of the benefits of this is if this isn't an inconsiderable amount of effort in order to create one of these models, that the amount of time it takes to train your system is effectively the product of the number of frequencies you can operate a core at, times by the number of combinations of those cores executing, times by the number of workloads that you're trying to characterize, times by the individual time for one of those workloads. So this starts to scale quite considerably. We've just seen that we can pull down the number of workloads from 60 to 20, for example, so make a reasonable saving. But by splitting this model out into the static part versus the dynamic part, it means that we can run all of the workloads at a single frequency and then run one of the workloads at various frequencies just to characterize the static part that's going to be changing. And you can see that the combination of these two things, with the original approach, it would take 40 hours to do this characterization, and with these two reductions, we can bring this down to 25 minutes. Error is marginally increased the result, but not significantly. One of the other benefits of this is it starts to become closer to the bottom-up approach. So we combine it with the bottom-up approaches. Because we've brought out the underlying causes of the power consumption into the model, you can start to see the contributions of voltage or static power consumption in the behavior that you're seeing. And also, if you look at the contribution or the coefficients of the different performance counters in your model, so the grey, these are all the different or a variety of the different workloads that it's been tested on, with the grey bars being the actual measured power consumption and the colourful bars being the different coefficients, it allows you to see what contribution the static power makes, but then you can also see what contribution has been made by individual performance counters. Now, because of the approach we've taken to building this stable model, you can actually get some insight as to where power is likely to be being consumed in your system based on the contribution of these different coefficients. So, for example, I think the dark red bars, or the dark red parts of the bar here, are level 2 cache misses. So for some of these applications, you can see there are quite considerable power consumptions due to this. In others, there aren't. And that can probably give you some insight as to where power is being consumed in your system. If you visit this rather long web address of powermon.ecs.soton.ac.uk, you can find out more about this. And we've made quite a lot of the information available to download. So first of all, you can download the tools that allow you to pull PMCs easily off the Odroid platform. The second section here, 1.2, gives you the tools to then run all of the model building, or the data extraction process from the board, so pulling out all the performance counters, running all of the workloads, and so on. And then number 2 is the software that builds the model from that data. Number 3, for those of you that don't know, the Odroid XU3 was a fantastic platform that contained hardware performance counters, so you could run an experiment and actually measure in real time what the performance was. That's discontinued, and they now have the Odroid XU4, which doesn't have those power sensors anymore. So what we can do is we can take our model from the XU3 that we've built, and you can now run it on the XU4 so that you do have, if you like, virtual power sensors that you can use. And so you can download that model, which you can then run on an XU4 and provides you with that information. And then there's a variety of tools where once you've built your model, you can drop them into the website, and it draws lots of graphs to show you the kind of things that I've talked about so far. Okay, but now coming back to Gen 5 and talking about how that fits in. As I say, the work that we've done on this is still reasonably early, and I think that the schedule today is very nice, and I'm talking a bit about the power model, and we'll say how we're starting to think about that model for Gen 5 and the early results we've got, and then Sasha's going to carry on and show you how you can take a power model of any kind and stick it into Gen 5. So the approach that we've looked at is effectively to pick our benchmarks or pick our workloads at the top. On the left-hand side, we then execute that on the hardware, we record all the data, and we build our model. In parallel to that, we execute the same workloads on a Gen 5 model of the same hardware. We record all the activity statistics, and then we compare the activity statistics with the performance counters that we've measured in hardware. A couple of observations come out through that process. I'll talk about them in a minute, but it may be that not all the performance counters are available in Gen 5, and it may be that there's some significant errors in some of them. So based on that, you may have to rebuild your model. You end up with a model that you can then plug into Gen 5 and use to get power estimation. So from the slides I gave you previously, our model of the A15 picks out 7 performance counters, these 7 listed here. And when we looked through the outputs from Gen 5, it wasn't easily obtainable to get performance counters for those 2 in orange. And so we decided to drop them from our model and rebuild the model just with the remaining 5, or actually 4, because one of them is cycle count. So after rebuilding that model, we looked at how accurate the model was, again, separate from Gen 5 at this point. The graph on the left-hand side shows you the similar results to before. The bars are slightly further away. The error is a bit greater. If you look at this, where are we? Down here, the percentage error changes from, 3 to 6, so it roughly doubles. But it's still a pretty good model in terms of its R-squared value and its fitness, etc. We wouldn't expect it to be as good as the original model. We've dropped 2 performance counters. They were giving it valuable information. And also, when we apply this model into Gen 5, it doesn't provide the opportunity to model the temperature or the voltage variation that our hardware model would have used. So we're not expecting to get as good measures, predictions of power. So we then built the model of the Odroid as closely as we could into Gen 5. I'm not going to go through all the detail on that. No, I think I will leave that in the slides that are available for you if you want to look into more detail. We ran 15 workloads at 4 different frequencies. You can see the equivalent performance stats in Gen 5 at the top. And then quite interestingly, as I said, we looked at the correlation between these 2 things. And we actually saw quite a lot of difference between the statistics that came out of Gen 5 and the performance counters that we were getting from hardware. So around 30% difference in the execution time taken to execute the workload, and about 66% for bus accesses. So there's a number of reasons that we anticipate that's caused by. Probably largely specification error in terms of the modeling of the Odroid platform compared to the real Odroid platform. Some of the work that we're doing at the moment that my colleague can talk about with you later on is then using this information to identify where small improvements in the model can be made. But the interesting thing is then when we look at the output of this, the model power consumption between hardware in light grey, or hardware model in light grey, and the Gen 5 model in black, we actually don't get these really, really considerable differences in power consumption that you might have expected from the previous slide. And actually, we're in the order of 10% off in most of these. And that's for a couple of reasons. The first reason is because the model is formed from both the static power part and the dynamic power, and the Gen 5 events or the performance counters are only really contributing to that dynamic part, the switching part. So the static element of the power consumption remains more accurate and unaffected by those variations in Gen 5's, or the difference between Gen 5 and the PMCs. Also, I think they have a tendency for some of these errors to cancel each other out. So it's probably completely against what I said earlier on about having a stable model, in that there's just some luck here that the difference in values means that it approaches a reasonably accurate prediction of power. One of the things that reinforces that point about static versus dynamic, if you look at the errors across different frequencies, operating at a lower frequency is giving a more accurate power model, likely because the static power consumption is contributing a greater amount at lower frequencies than at higher frequencies. Okay, so there's kind of 2 parts that I've talked about there. The power modeling methodology itself, and it's really formed from these parts of picking the right workloads to test it with in the first place, selecting those performance counters, and then building the model that is a closer representation of hardware, and then applying those to Gen 5. As I say, the tools are available, and I should also add that I'm certainly not the only person to talk about this work. In particular, Matt Walker, sitting in the back corner of the room, is his PhD that's been looking at this, and he's got a poster this evening and tomorrow. So if you've got any really nasty questions, I suggest you go and ask him instead. So that's all I've got to say. I'm happy to take any questions.